Hi, everyone. This is Sebastian Traeger, Managing Director of Reliability Center, and welcome back to another episode of Reliability 4.0. As always, we're on a mission to help make the world a more reliable place. And today we are thrilled to be joined by Satyaki Ganguly with Wolfspeed. And we are thrilled he's joining us today. Welcome, Satyaki. We are really grateful to have you on the show.
Thank you very much. And thank you very much for inviting me here. Really excited.
So, tell us a little bit about the company and your role in the company. Let's just get started getting to know, what you do there and what the company is all about.
Absolutely. So I'll talk about myself. So I'm a senior reliability manager here in Wolfspeed. And as many of you probably know that Wolfspeed does this silicon carbide powered devices. So it's the way Wolfspeed works. So we have our own crystal growth and epi. So basically it's a vertical integrated process that we have our own silicon carbide epi, and then on top of that, we fabricate our own device. And it is both MOSFET and diode, and it has its application in various fields that we all know. But after the fabrication is done, we also do package our parts, then sell them in discrete, in modules, in all different forms. And we have die and discrete, all these things. So now that's the business aspect. Now from reliability side, we do support from our department. I support and my team supports the reliability of all these products that we sell. So basically any new product that Wolfspeed is planning to launch or it's launching from the MOSFET side, from the Schottky diode standpoint, and the module standpoint, the reliability qualification test is performed by my team. And so basically we'll get devices in package form, and then we'll be running different type of reliability tests. We have full reliability setup in Wolfspeed in our RTP area in North Carolina, and different tests. For example, as you know, HTRB, high temperature test, reverse bias, high temperature gate bias, then thermomechanical aspect to check temperature cycle, all these things. So we have the full setup here in Wolfspeed. We run all these qualification tests to qualify any specific product that we are planning to launch, and that is overseen by my team. So there are many real engineers, there are many technicians who are launching this test, and we analyze the data after the test is done. We look at the pre-post data analysis and find out how the devices are doing. Based on whether it's an automotive rated product or not, we run different sample size, as you know, based on JEDEC and ASE standard. Typically 3x77 is the sample size you need to do for automotive sample, and that's what we do for all these different qualification tests that we are running. So that's from the qualification aspect of any product, what we are running. Then my team also look at different aspects. Say, for example, any process change that is happening in Wolfspeed wide. Say you are changing the gate edge process, you are installing a new tool in your fab. What is the reliability implication for that? That do you need to do any specific test to understand that when you are launching any new process or any new tool, do you need any reliability test to perform to understand that that will be fine going forward to launching that? So my team oversees that and do understand or advise what kind of test needs to be done. And then we perform the test, do the data analysis, and go from there. So that's that.
Great.
And then, thank you for that. And then we also support various R&D activity because, as you know, this is a silicon carbide world that we are talking about. Now, for silicon carbide, people always compare it with silicon, and silicon has a very rich history for the powered devices, but silicon carbide has its own things that silicon cannot support. For example, the high breakdown and other things. So the reliability aspect or the reliability consideration for silicon carbide devices are different from silicon. So we need to do various R&D study to understand what is different between silicon carbide and silicon. For example, in terms of gate oxide reliability question, from high voltage reverse bias standpoint, what are the new things that we need to do? So basically, there are a lot of new learning for silicon carbide world. And we do a lot of new DOE that we perform, new real science that we try to uncover so that we get more learning, and that will be helpful for our new test of the going forward for the robustness of the product. So we done those kind of experiment. We do publish in conferences, in journals. We show how things are moving for silicon carbide in general. We do support various activity from JEDEC standpoint, meaning we do participate in JEDEC world to write new document for silicon carbide qualification standard that we are actively participating and showing. So my team, myself, and my other folks are taking part in those meetings and writing document for silicon carbide qualification. So those are the main aspect that we are looking into it.
That's a lot. That's a ton. So
Right.
your hands, it sounds like you all touch because you're involved in the R&D and then you're also involved. It sounds like once there are beyond prototypes, but actually production ready products and everything in between. So you really are
That's right.
looking at that full life stage of the product. So
Exactly.
we're gonna drill down a little bit more into that. But before we do, I always like to just provide a little background on folks I'm talking to. What is your origin story of getting into the kind of reliability engineering space? How did you end up in this world?
Yeah, thanks for asking that, Sebastian. So yeah, so that's an interesting story. So I did my PhD from University of Notre Dame back in South Bend, and I did it in gallium nitride really. So my role there that I learned to do AP growth of gallium nitride. I also worked on the device physics aspect and other things that how to fabricate a GaN transistor and how to make that and how that works and everything. So that was part of my PhD work there in back in Notre Dame days. But at that time, as you can understand from university standpoint, when I was growing my devices, GaN devices on silicon or silicon carbide and all these things, to publish a paper from university standpoint, you think, well, I have a say 3-inch, 4-inch wafer. You get 3 or 4 working devices. You said, oh, great, that's my paper, and that's my work is done. I have demonstrated something great, and that's amazing. So from technology standpoint, that's what I was doing. So I did not have any exposure to reliability at that time. But after I was done with gallium nitride, the next step that I took in my career, I actually went to Intel because I also wanted to learn about the silicon side of the world's best fab that's in Intel, Oregon. And I wanted to see how things are run there. I spent some time in Intel 3 years and I working in the device group there to find out what are the different failure mechanism that's happening when you are going to make a 10 nanometer node, a 7 nanometer transistor. What are the different fabrication challenges that you can face? So those are the work that I was doing. At that time, when I was spending my time in Intel, I got an opportunity in Wolfspeed, and they were looking for some person who will be interested in reliability but knows the device very well. I said, well, that will be my opportunity because so far in my life, I was working with devices and I did not care about reliability. It's all about other aspect of that. But reliability is really one of the heart of the industry, the way things run. And I got an opportunity to come here and to explore that. And then I came to Wolfspeed. And at that time in Wolfspeed, they were supporting both gallium nitride devices for RF and silicon carbide reliability as well. So I got the opportunity of working in both the side and develop here. And that's kind of gave me everything for all these different semiconductor, gallium nitride, silicon carbide, and then the reliability aspect, that how reliability comes into play. In a wafer, if you have only 4 devices, yeah, that's great from a technology standpoint, but that's not a reliable product that you can go and sell. And then I learned that how to make a product reliable, or what are the challenges that people face to have a good yielding wafer, and at the same time the reliability is delivered out of that. So that's then I started to grow here. I started as a senior staff reliability engineer there, then became principal reliability engineer, then the senior manager. So that's a natural career progression here. That's
okay. That's great. So you mentioned that for you saw reliability is the heart of some of the work. I would think with semiconductors, regardless of what type, because there's so much high tech going on, that's what all the energy would be. But so why do you think reliability is so important? Because I would imagine performance is what everyone's focused on, right? Making things smaller and more powerful, et cetera.
Absolutely. And that's great. And that was my perspective before I really came here, right? Yeah. When you are demonstrating a technology, yes, your first goal will be to making your first device. That if it works, yes, you have proved your concept. But then the next challenge is, yes, one device won't be, if you have just a very few devices out of a wafer, that's not profitable. From a company, you'll have to think from a company standpoint or from a manufacturability standpoint. If you have demonstrated one device, that's great, but it does not mean that it is repeatable across the wafer, and then it is reliable, because these products or these dies will be used, say, for example, in high temperature application, will be used in high voltage application, based on what application you are talking about. So demonstrating is one thing, but then you will have to prove that these things are applicable for a specific application, for a high temperature, high voltage, or even for high altitude. Some of these devices will be used for example, in spacecraft, right? And there, if you tell them, well, I'm saying a nice device, which works great, but well, if it goes at a very high altitude and a different temperature, I don't know how the product is going to behave. You might get a crash in your aircraft, and that's not acceptable, right? So you have to prove that the reliability is the heart of this driving force of this different technology that we are creating at this point. So I think this is a big part of the generation that we are in.
That's good. So on that, sticking on that idea, so you having to test these devices in all these different settings, what tools are indispensable to you in doing that? How do you determine if this wafer is going to work in space as well as high voltage or whatever the applications are? How do you go about testing that, and what tools are you using?
Absolutely. Yeah, very good question for that. Now, whenever we release, or any company or any manufacturer release a product, they know what will be the application, what will be the target application, right? So from that standpoint, at least when you are releasing a product, you know, typically at the early stage, you know what will be the typical application that you are targeting for that. Say, for example, as I mentioned, that if you are targeting for this at a very high voltage space, then you know that you need to test the reverse bias capability or blocking capability of that device. You need to at least test this kind of devices for long hours at a high voltage condition. So you know what kind of tool to use. Now, there could be certain other application where you don't need to use for a very high voltage, but you need very high temperature, where thermomechanical aspect will come into play. In those areas, you will do some other testing, for example, temperature cycle, where there will be a huge temperature swing in, say, between night and day, where you are using your device, that you are going to see a huge temperature swing. Then you should test those aspects of the device before you release that in the field or that specific application. So it will be driven by that.
That's good. That's helpful. That is really helpful. How, obviously our company cares a lot about this root cause analysis. How does root cause analysis come into play there, given the types of materials and applications you're using? Is it even a tool that you use? How do you use it?
Absolutely. So root cause analysis, I think, is the most important part after you do the reliability testing, for obvious reason, right? Because, say, for example, you are trying to qualify a product for any application, you won't get a first pass success most of the time, right? There will be some failures. When you are trying to do a qualification at the very early stage, when you are demonstrating the feasibility of the technology, there will be reliability failures. And when the failures will happen, you will have to understand that where this failure is coming from. So then the root cause analysis will come into play. And you will have to understand that, well, okay, in which layer my problem is. Is it related to fab, for example? Is it the fab process that's causing the problem? Is it the packaging, for example, after that you do? The packaging-induced failures are happening. Unless you know that precisely, it will be very difficult to go to your next phase or to have a next robust device from that phase. So yes, root cause analysis, I feel, is the heart of that.
Okay. Yeah, that makes a lot of sense. From an innovation perspective, obviously you're in a very innovative field, but what I'm curious about is not necessarily the product innovations that are happening, but where are the innovations around either the tools that you're using or the way you're going about testing for reliability? What are those innovations that you're seeing?
I think it's both. It's basically both. So you definitely, as the technology innovation is happening, at the same time, you need your tool innovation to happen as well in parallel. And basically what I mean by that, I can tell you one example. Say, whenever you are making the device, it's just a different example, smaller and smaller, for example, and that's from the CMOS side. But here, even for power side, I can tell you, the more challenging product that you make, say, for example, you want to get a very low RON and very high voltage capability on the same device. And say, for example, you are looking for high power deliverable, you need to go at a very high temperature, all these things. Then you need to look at every aspect of the material that you are talking about. Say, for example, silicon carbide, the more aggressive approach you are taking, you might be getting more defects that you will have to fight against. Now, whenever there are higher defect count or stuff in your AP and other areas that you need to screen out, you need to have a sophisticated tool to find out that what kind of screening that you should be doing or spending money, so that whenever going into the fabrication phase, you are not impeded by those kind of crystal defect or, for example, your AP defect. You should be having a very sophisticated tool by doing some kind of inspection, automotive or automated inspection. You should be able to screen them out even before they go to the fabrication phase. So we need some kind of tool innovation at the same time that will be large volume and at the same time would be precise to find out this kind of defect even before we go for the electrical testing. That's one aspect. That's just one example. There are many other examples.
Right.
For example, yes, right. So for example, even for reliability tool standpoint, whenever the mission profiles are challenging, for example, say you are doing something where the humidity will be very high, your voltage will be very high, and there will be a very high switching speed that you are looking for. You need to have some kind of dynamic system that will be able to test your device, which are switching at a very high speed, should be able to give you high voltage, and at the same time should be able to give you reach a very high temperature and humidity. So you need the tool innovation as well, so that it can support those kind of reliability at the same time. So it's basically both needs to happen in parallel.
Well, great. Well, there's so much I feel like we could be talking to you about. Unfortunately, these always come to an end, but I do have two more questions for you. The first one is actually one I like to ask at the early stages, and that's actually, let me start with this one. I want to just say, what's kind of one final word you want to encourage folks around when you think about your expertise in the reliability engineering space? If you're thinking about communicating to somebody who's maybe new into the reliability engineering world, what advice would you give them based on your experience and expertise?
Sure. Yeah, that's a good question. And I always felt about one thing. That's okay. One of the heart of reliability engineering is a lifetime projection. We all know that well, if the product people say or the technology innovation people are doing that, whenever that will be applicable in real life application, that what is the lifetime in my application space, in the use case scenarios. And to do that, to do this kind of lifetime projection, what people do, they will do at very high voltage or high temperature testing, basically at the accelerated condition. They always want to test the device. And then based on this accelerated result, people try to project what happens at the operating condition. That's typically the way industry goes. We'll always have to understand you just cannot go too much accelerated condition and you generate some failure mechanism or more that's not really relevant at operating condition. So you need to understand the physics very well so that when you are trying to accelerate to get this kind of failures that will be relevant for operating condition, you need to understand the physics so that you don't accelerate too much. That will go to a regime that will cause failures that's not relevant at operating conditions. So that's the advice, that before you go there, make sure you understand that physics and don't go too much.
Yeah, because you might be creating scenarios that are never going to occur in the real world.
Absolutely.
The other question, and normally I'd ask this at the beginning, but I always like to get a little bit of a sense of folks on this podcast. What do you like to do outside of work? What are some of those life activities you just enjoy so we can get to know you a little bit better?
No, sure. Yeah. So other than reliability science work and all these things, I have two little kids who are 3 and 5 years old. I enjoy spending time with them. And I mean, of course, with my wife, we do go out a lot. We do hiking and we do love hiking and go to many places. And I'm a big sports enthusiast. I do watch soccer, football, and also cricket as well. I used to play cricket a lot during my college days, which I don't get much time at this point after all this responsibility. But whenever I get time, I go and do play that with my folks.
That's great. What do you think of, what's the name of the fast cricket?
So that's called, yes, exactly. That's called T20.
Okay.
T20. It's a 20 overs format. So when cricket started, it was a test cricket. Basically, it's a 5 days long cricket. Then it was a shorter version. It was 1 day cricket, meaning it is still 7 hours version. Then people say, oh, well, that's too much. Now, when you look at the American sports, baseball, basketball, everything, we need to compete with that. Then now there is a 3 hours format of cricket, which is called 2020. 120 balls for one team, 120 for the other. And then that's the way it's a 3 hours version of that. That's
what do you think? Do you enjoy that, or are you just hey, if it's not 5 days, I don't even want to pay attention?
No, I do enjoy that, because again, it's kind of reliability, because things are progressing, people are having more demand, they don't have much time. At that time, you want to be entertained, and at the same time, you also want to show the skill. So from those standpoint, T20 is kind of a compromise between that. I don't want to go it in a shorter version from 2020. I think this is what it is, and it's okay, and people will adapt, and there will be more amusement or more entertainment out of that.
That's good. Well, great. Well, thank you so much for the insightful conversation. Again, we've had Satyaki Ganguly here with us from Wolfspeed. It has been just a pleasure talking to you. I mean, it's unbelievable how much knowledge you have. And for you to be able to take some time to share it with us, we really appreciate it. This whole podcast is about helping reliability engineers and really anyone take steps to kind of closer understand how they can put in place a more reliable culture. And so for all those listeners out there, especially if you're looking for RCA training or resources and materials, we encourage you to check out reliability.com. If you want to dig deeper by using software, check out our Easy RCA software. And again, we're just so grateful for our guest. And that is all the time we have. We hope that you'll see us on the next podcast as we continue our journey to make the world a more reliable place. So thank you all, and we'll see you on the next episode of Reliability 4.0.
Great.
All right.